So now we're going to use this AOV command. It works a lot like the LM command in that it works best if you save the result of it into a named R object. So just try running this code, either pressing the play button or Control Enter, and let's see what happens. So nothing prints out in my console, but over here in my environment, I now have a new object in my data section. So I haven't been able to see anything yet. The useful thing that we're going to do is run summary parentheses and then the name of our model object. And I've just given my model object this kind of dumb name, A1, for like ANOVA 1. You could be better than me and you could come up with a smarter name for your object. It doesn't have to be called that, but that's just my default. And then if I was going to make another model, I would call it A2, A3, etc. That's just my practice. So we're going to do summary of A1. If I Control Enter here, I get the ANOVA table. So this should hopefully look pretty familiar to you. It has a row, which is the row for the groups. It has a row, which is the row for the residuals. It doesn't have a row for the total, but you can always figure that out by adding things up. So let's just read off the table. The degrees of freedom for the groups is 4. So that's from right here in the DF column. And that makes sense because we said we had 5 groups. 5 minus 1 is 4. The error degrees of freedom is 1376. So I'm just reading that off the table. And then the total degrees of freedom, that needs to add up. 4 plus 1376, 1380. So we've got all our degrees of freedom now. And then the next question is what the test statistic and p-value are. Again, we can just read this off the table. I don't know why it's behaving like that. So the test statistic is, our test statistic is the F value, which is 2.752. The p-value is 0.0269. And then what is our generic conclusion? Well, we reject the null hypothesis because 0.0269 is less than 0.05. We have evidence to suggest at least one mean number of hours worked is different. But the thing that's annoying with ANOVA is that's all it tells us. It just says at least one of those means is different, but it doesn't tell us which one. So that's why we would want to go on to some inference after ANOVA. Really don't know why it's doing that. And the inference after ANOVA is once you have found a significant p-value, you've rejected the null hypothesis, you've concluded that at least one of the means is different, then we can do inference to figure out which ones are different. So this is basically like doing inference on a single mean or inference on a difference of means, but we're going to use the square root of the mean squared error. So that's from the mean square column down here for the residuals, which are the error. So the mean squared error to estimate sigma rather than using the sample standard deviation. So if we had a difference of 2 means, then the standard error would be approximated by the square root of the mean squared error times 1 over n sub I plus 1 over n sub j. So if we wanted to find the difference between the number of hours worked per week by divorced people and married people, we would need the mean squared error. So we would do like the square root of 208.6 times, and then we would need 1 over n sub I plus 1 over n sub j. We'd need to know what those sample sizes were. So I could scroll back up and find that tally code and just copy that. And then let's bring it back down to where I was working. And it looks like I've got 403 people in the divorced category and 998 in the married category. So I could just substitute that in here, 403 and 998. So our estimate for the standard error is 0.85. That would be our best guess. And now we could use R as a big calculator like we have on some of the previous labs, and we could figure out the confidence interval by hand, but it's going to be easier to use a convenience function in R. Oh, well, let's just think about the degrees of freedom for a second. We need to use the degrees of freedom for the error, which in this case is the error degrees of freedom are 1376. But now we're going to use this function in R that's going to do all the pairwise tests all at once. So if you do a bunch of tests at once, you can run into this problem of multiple comparisons where you could end up with a family-wise error rate that's much larger than your standard alpha level. And one of the solutions to this problem is the Bonferroni correction. So let's say you're going to do 10 tests. You just take your alpha level and you divide it by 10. So if we had a regular alpha level of 0.05, we knew we were going to do 10 tests, well, we could set our alpha level down to be 0.005, and then even 0.005 times 10, we would only make an error overall 5% of the time. So in R, you can do a bunch of tests all at once, and one of the ways to do this is using Tukey's honest significant difference. So Tukey's HSD, it's similar to the Bonferroni correction. It's a little bit more complicated. It was actually John Tukey, who's a statistician. He was coming back at another statistician who'd come up with the least significant difference, and he wanted to call his the honest significant difference. So I'm not going to get into the details, but we'll just use it. And what we're going to do is we're going to create an 80% confidence interval for the difference between the number of hours worked by divorced and married people. I'm just going to run Tukey HSD, and you need to be careful with the capitalization because R is really picky about that. So you need a capital T and a capital HSD, then the name of your model object. So if you just run Tukey HSD parentheses A1, you'll just get a default with a 95% confidence level, but I said that I wanted an 80% confidence level, so I'm going to set that here. So if I control enter, I get a bunch of output. So it says it's an 80% confidence level, and then it has the output for all of the different pairs. So here is the interval for the married and divorced pair, and we could interpret it. So I am 80% confident that the true difference in mean number of hours worked by married and divorced people is between negative 2.92 and 1.81 hours. So basically, we are not that confident about who works more because that interval includes 0. Married people might work more or they might work less than divorced people. We don't know. And we could look at, there's intervals for all of these different pairs. And again, I've got the lower end of the interval, which is here, the upper end of the interval, which is here. But it also gives us a p-value for each one of these pairs. And it's an adjusted p-value. Again, it's using this Tukey's HSD, which I'm not going to get into, but you can just look at it and see which p-values are significant. So if we think about all these hypothesis tests, we're just looking for the small p-values. So in this case, it looks like widowed and divorced is significant, and widowed and married is significant. Widowed and never married, that's getting close, but it's not quite, and then widowed separated. So the only three with significant differences are the widowed and divorced, widowed and married, and widowed and separated. We didn't actually see a significant difference here, and there was no difference between any of these other pairs. So that is what ANOVA is good for. At first, it's just going to tell you if there are means that, at least one mean that is different. And then when you do inference after ANOVA using something like Tukey's HSD, that'll show you exactly which pairs are different. And it'll do a correction so that you're not making a mistake more often than you want to.